neural networks for human motion modeling and character animation. We can present Rubén Villegas. He is a research scientist at the Creative Intelligence Lab at Adobe. He received his PhD from the University of Michigan under the supervision of Professor Anglak Lee. He is interested in understanding and modeling the mechanics of human motions for applications in character control, motion retargeting, character interactions, and general human motion synthesis. Rubén's research interests also include generative modeling of videos and images, model-based reinforcement learning, and robotics. Please, Rubén, you can start the presentation. You're welcome.
Yeah, hi, I'm Rubén, and yes, I'm a research scientist at Adobe, and I'll be presenting some fun works on human motion and character animation. So the main question I'm trying to answer is how do humans move? So there are many complicated muscle tendons and ligaments interacting with each other that allows us to move, as you see Carlton here. And also these interactions have to interact. These interactions have to be aware of the physical world and laws of physics and so on to be able to move well. And because of this, we're constantly balancing our body, and which results in highly complex interactions, which are very difficult to model. And so that's what we're focusing here. And so machine learning has been shown to be able to model this, to model very complex data by learning how it behaves in specifically neural networks. And so what will be the most promising approach to do this? And so the usefulness of human motion, if you can model it well, you can predict the future, you can transfer motion between humanoid bodies, and also you should be able to control some humanoid robots or something in that nature to perform certain commands. And so here's some example of future prediction. So here's just all these videos are synthesized given some previous frames. I think 5. We synthesize 25 frames into the future. And also motion transfer. Here's an example of some work back in 2018 CVPR. Where we can have this character follow this human motion. And another example is character control that I mentioned, where we just tell this character to just walk around or jog and stop and do certain commands based on trajectory inputs. Yes, so the first thing I'll be talking about is future prediction. So I'll be presenting some work from back in 2017. So this work is called Motion Content Network, or MCNet for short. And what we focus here is trying to separate motion signals from what's in the input frame, in order to synthesize future frames. So in this method, we have a convolutional LSTM that observes these image differences, temporal differences, and then this convolutional LSTM is expected to model the dynamics of this human input. And we have this content encoder, which just models the appearance of the human in the background and so on. And so we concatenate these two signals and give it to some layers that combine the signals together. And also we have some, you're probably familiar with, some residual connections going from the motion encoder and the content encoder that all work together with the concatenated encodings from LSTM and the content encoder to synthesize the future frame. So how we train this? So we train this using a combination, just some simple objectives. So the first one is image loss, where we simply just try to match the target image and also some gradients in the image. And then this GAN loss, where we're trying to full discriminator loss. So the reason we add this loss is just to make the images look as sharp as possible. And we have, of course, a discriminator objective where we just alternate between these two. So the objectives are not that simple. It's the neural network itself that is able to perform well, or are simple. And so here are some results on some trade model. So there's a single model for all actions in each data set. And we tested on the KTH and Weisman action data set. So we train on KTH, but also test on KTH and train and test on Weisman to kind of see if the model understands motion. So it should transfer between data sets that look similar. So here's some results, just some visual results for now. And so as you can see, we have a convolution LSTM baseline, which was back in the day what people would use. And yeah, so our method is actually able to identify the moving object in the foreground and separate it from the background, so the dynamics can be more focused on the object. And yeah, and it's able to model the video better. And here's some quantitative evaluations. And so the blue curves are our method, red curves are the convolution LSTM, and I add, just to be fair, some residual connections in the convolution LSTM architecture. So basically the difference is one of them models motion and content separately, the other one doesn't. And one of them has residual connections, the other one doesn't. So as you can see here, so here we have peak signal to noise ratio and structural similarity. So the higher the better, and the x-axis are the time. And so as you can see, our method is able to extrapolate frames into the future up to 20 steps here, and better than this convolution LSTM. And then we, just to see how far we can take our method, we go we test the the UCF 101 dataset, which has a bunch of humans doing different actions. We train on a different dataset called Sports 1 Million, and then we test on UCF 101 to see if it transfers. And back in the day, again, there were some methods. This Matthew et al. I forgot what it's called, but they are basically our method, because it can separate the foreground and background motion. It can perform better, but still, as you can see, it's not that great for this type of data sets, because the motion is much more complicated than KTH, and there's partial observability and background is moving, so it's really difficult to model. So again, just some curves here showing that, yeah, we're better, I guess, numerically, and than these other methods. The same evaluation metrics, PSNR and SSI. So yeah, separating human dynamics from image and content, from image content, helps us make a better long-term future prediction. However, deterministic prediction results in blurriness, because there's multiple futures given a single past that we can predict, even though maybe there's only one true future, but given the past, if you don't know the future, you can predict multiple futures. And so one thing we will explore in the next work is model capacity and other factors. Another factor that contributes to model this video better. On top of that, we also investigate inductive biases. So that leads us to this NeurIPS 2019 paper, where we study different inductive biases for prediction, just to see what's going to help us to continue in the future to be able to predict the future video better. So we look into simple convolutional architecture, convolutional plus recurrence, and also stochastic variables, and also model size to see if big networks actually help. And this is based on a network from Emily Denton from back in ICML 2018, but we've made a few modifications to improve the performance, which is make it fully convolutional, which I'll talk about next. So we have an image encoder, similar to hers, posterior distribution network. So it just estimates the parameters of a Gaussian distribution that we can sample from, and a prior distribution, which estimates the parameters of the same of another Gaussian distribution, but without observing the current frame in the video. So it's like a prior distribution, and we simply try to match the two during training, so that at testing time we can just sample from the prior. And then we have a deterministic decoder convolution LSTM, which kind of just moves time forward in looking at previous steps in trying to model the long-term dependencies between them. And also a decoder network that just grabs the output of this LSTM and decodes the image. It's a mirror architecture of the encoders. So here we actually experimented on multiple data sets, but here I'm just going to focus on humans. So if you are interested, you can look at the paper. We do some robotic tasks and also some driving tasks, but I'll focus on humans. So yes, so here's just some qualitative results. So you can see here the humans. This data set is more complicated than the one that I showed before that was black and white, and this human motion is modeled well, better than the smaller baseline. So what we're showing here is the full recurrent convolution plus recurrence plus stochastic variables, but comparing the sizes of the methods. And I think this biggest one was like 800 million parameters. And this one I forgot, but it was very small. And yeah, so bigger networks perform better at this task. And here's just some. So this is the Frechet video distance metric. So smaller the better. And this is that I'm just comparing the number of parameters. And here's SVG prime is our method. LSTM is just without stochastic variable. CNN is without recurrence and stochastic variable. So CNN just completely fails. But the having recurrence and also stochastic variable just keeps getting better as we increase the number of parameters. And also here's actually this Frechet video distance. I should mention that it looks at the entire video as a whole, as a sequence, instead of looking at independent frames. The reason we do this is because the multiple possible futures. If you look at every frame and then you deviate a little bit from the true future, then you're going to get poor performance. So here we kind of look at the distribution of all the sample futures that we have in our from our network to look at the distribution and not just the independent frames. But also we evaluate on the independent frames, and so you can see here the same. The CNN performs the worst, and this stochastic variable helps. And here the X is the prediction steps, 25 steps into the future. And this is VGG cosine similarity, where the higher the better. And here's just some error bars because we predict multiple futures. So I'm just computing the, how much, like how worse the worst, how much worse the worst is, and how much better the best is. And this is the average. Yeah. And we also measured same PSNR and SSIM, which are similar per frame metrics, just for completeness. And finally, we use human evaluation just because it's very difficult to evaluate video, even with the Frechet video distance and all these per frame metrics. And we're showing that the biggest model is 98% of the time is preferred by human evaluator, so user study, versus the baseline, which is the smallest one, 1.3. And then when they think about that, they're about the same 0% of the time. And for the LSTM models and for the SVG prime models, which have the stochastic variable, the same effect, we see the same effect. So this actually indicates that we need better evaluation metrics because the current ones are not good. And so another question we kind of answered towards the end is, can we handle larger videos? So the videos that I show are 64 by 64 pixels, and we just kind of train our method with 128 by 128. And as you can see here, we can, and the videos actually look much better than the ones that I showed before. And if you, unless you look really, really closely, it's hard to tell that they're not real videos. Yes, so bigger models are a good thing to do, and the other inductive biases that I investigated. So yes, so what I just said, large fully convolutional neural networks equipped with stochastic variables model video as well. However, these representations that we're modeling, these pixels are very hard to interpret if you want to do something where you can control things. And so the next works, I just kind of model humans in their skeleton instead of pixels. And so for motion transfer and control related tasks. So motion transfer, so this is a work from CVPR 18, and where we want, the goal is given an input image, we transfer the motion into this target character here. And this is retargeted by our method. There's a lot of jittering, but that's how we did back then. So here, how we model this is we have a forward kinematics layer. So in forward kinematics, what it does is basically you have some starting pose like this one, and then you rotate each one of the joints until you get the target pose, target joint positions given those angles that rotate the joints. So we basically embed that in our neural network. So what we have is a neural network that a recurrent neural network that takes in some current pose, and this P1 is the local joint movement, and then this V1 is how the character itself moves in space. It as the hip as the moving coordinate system basically. And so yeah, we have this, and then we have another encoder RNN and decoder RNN that takes in this character in T pose, and we output angles and velocity for the next time step. Velocity, as I said, is the root velocity, and then we pass this to the forward kinematics layer. So the cool thing about this is that these angles are not supervised, but we have we don't have supervision here either. I'll talk about that next, but if you output something here, you can automatically discover the angles without supervision. So because the forward kinematics layer, it's it's constraining what you're doing with the input T-pose character. And once you rotate the joints, you have a perfect, you perfectly constrain the bones and so on. The motion itself is not that well constrained, but there's hard constraints in the bone lengths that previous methods couldn't handle are perfectly modeled by this forward kinematics layer. Yes, so then what we do, pass that motion back into the neural network and repeat this process until we get the full motion. But like I said, we don't have supervision for this, or we don't assume supervision because it's very expensive to get. And so what we do is a cycle Gantt approach, where given motion A, if we have if we retarget motion A into character B, that motion B should be able, with the same retargeting algorithm, should retarget it to motion A. And you can basically just do mean square error between these two because it should be the same, even though you don't know what this one should be in the middle. And the one reason that you don't know is because the different limbs of the characters may result in different motion, and also different shape of the characters may result in different motion than this guy, the input. So yeah, here's our network again. We have input motion, angles, retargeted motion, and then we pass it back into the same network, and we get we retarget it back into character A, and then we apply some cycle consistency loss, which this one should be the same as this one. And then we have another thing we found necessary is to add some twist loss because since we're working on the position space, it's easy to twist something and you still get perfect positions. So we added a twist constraint and also some smooth movement constraint on how the character moves through time. And then finally, what helps us retarget is we have this discriminator network that kind of models the distribution of how this character B should move. So we have other motions where character B is moving in different ways. So what the discriminator network should do is be able to learn the constraints of this character B so that whenever you retarget from A to B, you can, if you try to fool the discriminator, you should make this character B move like a character B, if that makes sense. So it's something similar to cycle Gantt, where you have a discriminator for the other domain, but here the domain A is character A, domain B is the character B, and you simply just kind of use this signal as supervision. That's a real, not real type of supervision, given what the character B should behave like. And so we're training set, we use the Mixamo data set, and we have all these cool characters. And then the test time, we have these 6 characters, and these 3 are not seen during test time. And here's just some video that I show if it plays. Oh wait, I'm looking at the wrong screen, sorry. Yes, so I'm retargeting motion from, so yeah, one thing, we use a baseline of simply copying angles. That what I said, that you can just copy the rotation from character A to character B. So the baseline, you can see this foot floating artifact, and also yeah, the feet are floating because the motion is not modeled. The characters are different, basically. Same here. There's foot float. Well, our method, the foot is on the ground, and then yes. So basically, so our method is able to perform this retargeting in a fairly reasonable way. And then we test it on humans. So we don't train on humans. We train on the Mixamo data set, but then we just transfer this and just test it on humans to see how it performs. And then we also get some reasonable outputs, even though we never trained with human data. These are the what I showed before. And all this is done by just modeling this 4 kinematics layer and cyclogram approach for retargeting. And yes. So yeah, there's still some problems which I will address. And I mean, it's some current work that addresses this. So there's a brief sneak peek because yeah, this is work in progress. So can we do better than this? And yes, we can. So here's a bunch of characters dancing to the Macarena. So one thing I want to point out here is that so the previous method doesn't model shape constraints. Like the character could penetrate its own shape, and it will be okay because we just modeled the skeleton, and also it doesn't model foot contacts. So here we do all of that, and yeah, and it's just here like there's no foot floating as we saw before, and then the characters kind of know that they have a shape, so they don't penetrate their own shape. Yeah, and then this is dancing to the Macarena, which has a lot of self contacts and contact with the ground. And yeah, so here's just some comparison against some popular motion retargeting method called Human IK. So yeah, one thing I want you to pay attention is that what I said, that like the Human IK also it only does retargeting by considering the skeleton and doesn't know anything about the shape. So you will see problems, and I will try to point them out here. So again, the hand goes to, like I said before, the hand goes to the body. Well, our method knows that it has a body, so the hand just kind of stays within its constraints. And also foot contacts, which I mean, it's not a novel there's many methods modeling foot contacts, but I guess this is the first one with the models foot contacts within the neural network in a way. So yes, and the other feet are not floating, but yeah, there are a few problems still, and this is because we're not modeling the fingers, but that's probably hopefully we'll do that later. So the fingers here, it's simply they're not modeled by the neural network, and that's why you see some penetration there. But yeah, something that we need to still improve, but it's doing a good job at this. And here's another example. So this Human IK, the hands of this guy are in the leg, basically. Well, our method knows that it has legs and that it doesn't penetrate them. Yeah. So yeah, and here's another example. And here, this Human IK method, the hands just go through the face, while our method knows that it has a face. And again, so just to be sure that it's clear, it's this. The reason this happens is because this character's arms are longer than this character. So if you simply just kind of like look at so this method a little bit kind of copies the rotations. So it doesn't consider the body, the whole body. So if you do that, it's very likely that there's some mismatch in the motion. So in that method is also not aware of the character mesh. So, and the reason these self contacts that I show here are important because, for example, here we know that if we have some other method, if we just use this to model human motion instead of, doing this retargeting, here we can kind of have another method to detect that this person is kind of like concerned about something, well, by looking at the mesh and looking at the skeleton and so on. But here it's very very difficult because the hands are already in the hat, and then you need to maybe infer the context if there's any context here, but it's going to be difficult because the hand's going to be in the mesh, and you're going to have to do some maybe some heuristics or something that it's probably doesn't generalize. While our method, the contexts are there, and you can tell that this guy's concerned about something. And then here's also human motion. We can also model this with our method, and yes, and foot contexts are kept and so on. Yes, so this is cool because we control the humans, and also we can synthesize pixels in a different way because we're rendering them, and it gives you those cool animations. But yeah, can we take this a step further? So not just copy motion, but synthesize motion. And so this brings us to character control. So this is actually a product from Adobe called Adobe Aero, and I invite you to try it out. We have a feature called directable characters, where you have this guy and this girl, and then other characters that you can kind of do things with. And so there's a neural controller in there. So it's a neural network kind of making the character move. And basically what it looks like, I can't put all the details here, but what it looks like is we have a trajectory input, and then we have a controller that takes in the frame t and then produces frame t plus 1. And there's a bunch of things going on here. But yeah, basically that's what the controller looks like on a very high level. And these trajectory inputs include actions like, like whatever wave or whatever you want to do. But even though currently in the app, these waves are not modeled by a neural network, but that's coming hopefully in the future. Yeah, so this is what the app looks like, and maybe I can. So what's happening here is there's this demo. These characters are just following this burst around. So behind the scenes, what's happening is there's a trajectory being generated that's pointing towards the bird, and then these characters are just following those birds. And yeah, that's basically what's happening here. You can make them do other things than that. It's just up to your imagination, but you can just go to Adobe Aero and then kind of make them do whatever you want. Not whatever, but just play with your imagination. Yes, and yeah, so this basically concludes my talk, and I guess some future work that we're looking at are modeling contexts with objects, so similar to what you see here on the left, where the characters know they don't just know about themselves, but they know that there's a world around them that they can interact with. We kind of point in that direction by the foot context with the ground, but that's the world is way more complex than just ground. So our plan is to work on this type of interactions. So, and then another route is to kind of either model the physics that you see this character doing here. So it's a method that can synthesize the physics well. Or the other route is, some of you may know, is the reinforcement learning route, where you have an agent, you have a physical world that you put an agent that is controlled by a neural network or now it's neural networks are popular for this, so controlled by a neural network, but it could be something else that we might find in the future to be useful, so that these agents can act in the world. And this is all the research that we have going on at Adobe right now to kind of look at both directions, model the world, or figure out how to act within the defined world. And yep, and that's basically the end of my talk. And yes, thanks for your attention. Please, any questions you may have.
Okay, thank you for the presentation, Rubén. I think we have time for a couple of questions. Meanwhile, I have a question. I was wondering about the time for training these kind of models. Maybe you can comment about it. Rubén, can you hear me? Hi.
Yeah, so
okay.
I haven't looked into it. So we're looking into modeling hands, so that because of that, because you can, like, people, read hands and express themselves with hands. So yes, that's some we have ongoing research, not related to the character retargeting, but more in the human motion estimation and human, like, motion modeling and pose modeling and so on. So we are looking into hands as well. Yeah. So the reason hands. Oh, he can't listen to me. Okay. So how can hands? Let's see.
I think you can listen to me, Rubén, right?
Wait. So how can? Oh, they can hear me. Okay. Yes, the audience can hear me. They say. Okay. Yes. So. Okay. Cool. I thought that you guys couldn't hear me. Okay. Yes. So we're looking into hands and for other tasks. And yes, how much domain knowledge should we put into our models' thoughts? So it depends. So I guess maybe my one example is my I guess some people that I've collaborated with, they would want to discover everything from data just using neural networks, and it's possible, but I mean, if we have some knowledge that we already know is true, I mean, I've had kind of like, I've gone from one side to the other, where I think we should include as much knowledge as we can, and then let the neural network work within that knowledge, because it can constrain the network, because there's so many ways that it can solve a problem that sometimes they solve it in the most trivial way, then the network doesn't really work. But yeah, like in this, for example, in this retargeting, the forward kinematic, knowing that forward kinematics moves in poses the body is a good like not domain knowledge to put into the characters. But yeah, it depends. Yeah, I wish neural networks, we figure out a way that neural networks can discover everything on their own, but so far I don't. At least that's from what I have seen, it's not happening yet. So I haven't observed any. I mean, the only problem is, how do you get the resources? At least that's, I guess, the only problem that I face. And also, oh yes, I guess another problem is to kind of be able to parallelize over multiple. So to make the training faster, you should be able to parallelize over multiple devices. So actually, for that high video, the high fidelity video task, I modeled during training time. I was using 30 TPUs, 16 gigabyte TPUs, in one TPU per element in the batch during training. At test time, you can just use one GPU, but that's the only kind of like the only problem that I had to figure out how to solve is just parallelize this, because otherwise training these huge models, it's very time costly. Back then I could not do it on, even if I parallelize on GPUs, I couldn't do it, so I had to parallelize it on TPUs. And yeah, thankfully I had access to that, which maybe not many people do. But and I mean, I tried testing my first the motion content network. I tried testing it for action recognition. Oh, with a person in Mars for real time. So I think so. Currently, if you're talking about the motion retargeting project, currently it runs because it runs at 3 seconds per frame, but that's because it's a PyTorch implementation. I would assume that if you make a C++ implementation, it will be much faster. So yeah, my implementation runs to 3 frames per second, which my implementation is really, really not optimized for the shape aware retargeting. Not the retargeting from CVPR 18, but the recent work that we have as an ongoing work. It works at 3 seconds per frame.
Okay, Rubén, thank you for the presentation. It was quite interesting. I think you can hear me now. So we can continue with the next part.
I can't hear anyone. Oh wait, hold on. Oh, I had my volume down. Sorry. So what did you say?
So thank you for the presentation again, Rubén. It was very interesting. So we can continue with the next part of the program. We have a mentoring session. Okay. So thank you very much again, Rubén. We can continue to the next part of the program. Bye-bye, guys.